Y'all, here's the first lesson of the quarter. We're going to go over summation notation and this idea called Riemann sums, which really just applies everything we've been talking about, areas under curves and everything, and finding the area with a lot of shapes. And then how we're going to do this is actually familiarize ourselves with summation notation in order to look at better ways to write out different expressions. This isn't something that we're really going to go super in depth with, but I do think it's important that we know where the Riemann sums come from so that when we start doing more calculus-based exercises, we'll be able to appreciate how much easier it makes our lives. So just going to start off with summation notation. Just a quick review from what we did last time. We know that if we have a sum, it's represented by this thing called a sigma, this expression called a sigma. So it's just a Greek letter. It means add up all the values that you see. What the next part we have is our beginning value. So in this case, our k is equal to 1. So this is where we start, starting value. And then we go all the way to the top number, so 3 in this case, which is going to be your ending value. So this is the unfamiliar part. We have a sum starting at k equals 1. We need to keep in mind we always add just 1 to it each time. So we'll have a k equals 1, then we'll plug a k equals 2 into our statement, and then a k equals 3 into our statement. We call this thing a dummy variable because it doesn't really matter what symbol we use here. We could use an x, an I, a j, a k. Standard convention is usually I, j, or k though. So in this example, we're going to just do a k squared. So this is basically saying the sum of k squared from k equals 1 to 3. Or k equals, the value of k equals 1 to the value of k equals 3. So all it really is just putting in each of our values. So we have our first one that we start off with, 1. Then we add 1 to that value, plug it into our equation, so we get 2. And then finally we do that one last time, and notice how we ended up at 3. So we started here, we went all the way up to here. So then it's just a matter of simplifying this expression using some arithmetic. So we know that 1 squared is just 1, 2 squared is 4, 3 squared is 9. So we just add them all up, and we'll get a value of 14. So another way we can see this is by looking at a sum of values and coming up with a shorthand. This is usually pretty useful if we have a long list of numbers that are added together and we kind of just want to make sure that we have some nice, neat notation in order to do this. So for our second example, we're just going to go over that. So maybe I have an example like 2 squared over 4 plus 3 squared over 4 plus 4 squared over 4 plus 5 squared over 4. And so we're thinking, all right, well, if we have this sum, we need to figure out how to write it in this format. So first off, we're just going to put our sum symbol right here. This is saying I'm going to add up some amount of terms. Next thing we need is our starting value. So here I can choose any variable I want for the function. I'm going to just choose a j in this case. So j goes from some value to the next value, to some, and it ends at some value. So what you want to do is kind of find the pattern here. We know that our 4's are always repeating in the denominator, so we know that our general function is going to be some fraction with the 4 in the bottom. And then we take a look at the numerator. We notice, okay, well, we have a pretty consistently changing value that increases by 1 each time. So we want to find that pattern. If it's not immediately obvious, we might want to rearrange the different terms so that we do get an increasing pattern. So we start off at the beginning, noticing that we begin with 2. So this is saying from j starting at 2, notice how we add 1 every single time until we end up at 5. So starting at 2, going to 5. And so we're going to have a placeholder. We know that these values, it was some number squared each time. If we refer back to the value or the variable that I decided on, it was j. So we're going to want to make sure that this stays consistent, j squared. So now we have the sum of j squared divided by 4 from a value 2 to a value 5. And if we work backwards, we'll see that it extends in this way. So that's summation notation. It's a great way to represent different values or different sums in one nice, neat statement. We're going to see how that actually works for a function. So in this case, we're going to take. So we're going to talk about the Riemann sum. So the way we can do this, let's see how we should start this. So for the Riemann sum, this is just using summation notation to find the area underneath the curve. So I'm going to do a little bit of a setup here. It might take a minute or two, so feel free to fast forward a little bit. Once I put that check mark, I'm going to put a check mark right by here. Once you see that check mark, we're going to be good to go, ready to do our exercise. So let's go ahead and get that done. Okay, guys, hopefully you're back. What we have right here is a parabola represented by the equation f of x equals x squared minus 6x plus 13. So here what we were really doing at first was, so what we're doing with this is we're trying to find the area under the curve and represent it with summation notation, okay? So the easiest way to do this is to think back to our length times width argument. And we're going to kind of do it in a similar way as up here. We're going to write down the sum of the three areas, see what the common idea is behind them, so that we can stick it into a notation like this. So we start off with our first one, and we're doing this in between 2 and 4, with each of our little boxes representing that width. So we start off with our first rectangle, and notice how we evaluate the height at x equals 2, okay? So our red term is going to be the length times the width, so our length is going to be 1 times the height, which is going to be whatever our function comes out to at x equals 2. So we do 2 squared plus or minus 6 times 2 plus 13. And then we go on to the next one, and that's going to be evaluated at the left side of our box. So that's going to be our length, which is between 3 and 4, so 1 again, times 3 squared minus 6 times 3 plus 13. And then finally we have our last one, our last green box over here. Notice how we evaluated the height of our box at x equals 4. Oops, and this should be between 2 and 5. Apologies, guys. So that's this part right here. So we know that the width of this is between 4 and 5, so we have 1 times whatever the height is. So it's again putting it into our function, putting the 4 into our function. 4 squared minus 6 times 4 plus 13. So if you went up to someone and said, hey, this is the area underneath our curve, well, that would be fine, and we could simplify everything, but we wanted to get more familiar with this summation notation. So here we have a bunch of 1s going on. So we know that our pattern is going to have it's going to have a times 1 in it. But these ones, it might not be super obvious. So let's rewrite it in terms of our function so we can make it most general. This guy's going to become 1 times our function evaluated at 2. This one's going to be 1 times our function evaluated at 3. And finally, this one over here is 1 times our function evaluated at 4. So if we were to actually write out a Riemann sum for this, we could see it as the sum. We're starting at 2, so I, in this case, I'm just choosing I, equals 2, going all the way up and ending at 4. Now we have our general function. So here we have 1 times f of I, and notice how we have our general equation. Okay? So that's kind of all there really is to it. Nothing too difficult. We're starting at some value, we're ending at some other value. Okay? So just the concept is what we want to take away from this. The Riemann sum is the area underneath a curve. Specifically, it's as our rectangles get skinnier and skinnier and skinnier. Okay, so we have the concepts down. We know the geometry below. It's just a matter of getting used to this summation notation.